Hello everybody, my name is Ethan. Welcome back to the machine learning course here on Codecademy. In the previous episode or video of this course, we started the final section of the first chapter. So we're in the machine learning fundamentals chapter and we're on the unsupervised learning algorithms 1 section. And there's a bunch of different little articles and pieces of information that we have started with in the previous video. We did the introduction and then the k-means clustering parts of the section here. And now we're going to move on to what is PCA, or Principal Component Analysis. We're going to just jump right in. So if you missed this, make sure to go watch the previous video to get a better understanding of what that is. So right away, let's get into it. What is PCA? Learn how, when, and why to use Principal Component Analysis, PCA, as a part of the machine learning lifecycle. Introduction to PCA. In the world of machine learning, any model that we will implement will be more valuable when the features are engineered to suit the question we're trying to answer. With many datasets, we can simply include all available features, which gives us the full picture about our observations. For example, it's straightforward to see the correlation between height and weight for a patient dataset. Some datasets, however, have a large number of features. For example, our patient dataset expanded to include 20 different features. How would we visualize and correlate the data? When it comes time to actually process the data and train the model, we often hit computational or complexity limits. How do we leverage correlations within the data to make fewer, better features without losing the information included in the dataset? Situations like this are a great use case for implementing Principal Component Analysis. PCA is a technique where we can reduce the number of features in a dataset without losing any of the information we have. Sounds pretty great, right? This article will later cover, I don't know why I sometimes add words, but this article will cover various aspects of PCA, so let's dive in. Okay. Laying the groundwork for PCA. Before we dive into the specifics of PCA, we need to understand the importance of information. In particular, we need to understand how variance plays into the level of information in a dataset. For the purposes of this article, we'll be looking at the synthetic dataset about local pizza stores. So let's see what the data has. So we've imported pandas, we've imported matplotlib, pyplot, and we are reading in the data from pizza.csv, and we're printing the columns. So the output is an index right here, and the columns look like there are 1, 2, 3, 4, and 5. So we have a revenue column, total customers column, amount flour, amount tomatoes, and amount cheese column. Each row of the data pertains to an individual store and gives us information about how the store is doing overall and with their inventory and sales. Suppose we just look at revenue and total customers. We'll see the following information. So we see that revenue for different stores here has different columns. Interesting. In this scenario, the value for total customers has a value of 500 for every row. While every row has a value and therefore has data, this column does not provide a lot of information due to the lack of variance in the values. While we could include this feature in our downstream analytics, it doesn't provide any additional value because it would have the exact same data in every row. Now let's look at what the real data showed us about these two columns. If we just do this, revenue, total customers. Interesting. So we printed out, just look at revenue and total customers columns. But now if we show the real data for these two columns, we end up seeing that customers does change. So not sure what that's about, but as we can see, the real data set has far more variance in these two columns. Since each feature has significant variance, these features provide valuable information about our observations and therefore could be included and should be included in our analysis. Variance alone is one indicator of the level of information in a dataset, but it's not the only factor. To expand on the idea of variance within a dataset, we will look at the coefficient of variance, or CV for short. The premise here is that the variance must be taken into context with the central tendencies of that dataset. For example, if a dataset has a variance of 5, that will mean very different things if the mean is 2 versus a dataset with a mean of 100, obviously. Now let's calculate the actual coefficient of variance for each of our columns. We can do that by importing numpy as np, and then define the function to calculate CV, and that's lambda x, and we have the standard deviation divided by np, the mean of x. So standard deviation of x divided by the mean of x times 100. and then we use the apply function to our data frame to apply it. And it looks like the coefficient of variance of the revenue column is 10.0, 5.0, 9.1, 9.9, and 6.0 for all the following features. All the features in this data set have enough variance where they could be useful in analysis. Since variance is an important factor to PCA, these features will ultimately be ordered by the level of information, i.e. the variance, they have. For this data set, that means in order of importance, we'll look at revenue, amount of tomatoes, amount of flour, amount of cheese, and then total customers. While the results of PCA won't resemble our original features, this will be a mathematical representation of the information contained in the original features, which have a value for analytical purposes. All right, we have a coding question. So the kind of information we can vary from data set to data set, and thus the coefficient of variance, and thus can the coefficient of variance. Use what you have just learned on the news set of synthetic pizza store data, pizza news.csv, calculate the coefficient of variance for each of the feature in the data set, then create a ranked order in Python for the features in the data set in terms of information per PCA, most important to least important. So it wants me to, let's first run the code, get an idea of if we end up actually wrapping this in a print line, we'll end up being able to visualize what the head of the data set looks like. Okay, that's interesting. This is going to be a little bit harder because it's so much smaller of a little window here, but we can work with this and see that the same 5 columns exist here: revenue, total customers, amount of flour, amount of tomatoes, and amount of cheese. And we get all this information right here, right? So we want to first load in the data set, which we have done, and then we're going to calculate the coefficient of variance for every feature. So that was that interesting, taking the standard deviation of the variable x, and basically I believe what they did was they did the lambda x, and then they did the standard deviation, so numpy.standard deviation of x divided by the mean of x. Now there was some other interesting stuff that they ended up doing with that, so I'm going to go back up just to look at it again. So they calculate it by doing lambda x and then standard deviation. This is an interesting DDOF. Don't know exactly what that means. I wish they would have just a little explanation, and I did forget to multiply it by 100, so that was a definite mistake on my part. So I can do that, and I'll add the second DDOF is equal to, I believe they set it equal to 1 in this case. And we're going to set coefficient of variance equal to this expression, and then we're going to be able to use this apply function for the data frame, and we can do data frame dot apply, and then we use the CV. So this is going to hopefully multiply everything within our function, or find the coefficient of variance, right, of our function. And now rank in order of highest to lowest. So now if we were to print out this this statement right here, we'll wrap it in a print line here just so we can see what's happening. I'm also going to just unprint or stop printing out the df.headline so I can just see what we're doing here. It's interesting how it's running it twice, and I don't know why it's doing that. It is end up running the code twice, which is a little strange, but we get the same answer, and we're now going to rate that in based on importance. So what we'll do is, I assume it's a pandas data frame, so we can just select the second row. If we do we'll do 4. I was thinking of doing a bit of a for loop possibly, and then ranking them in order of importance from highest to lowest in a list. You could obviously just automatically do this, but I would want to do it in a way where it automatically updates based on the... We'll just do that for fun. Yeah, I don't know why it's running it twice. It's a little strange because we only have it in the code one time. So rank in order of importance from highest to lowest. For right now, what we'll do is we'll just kind of hard code it, which is fine to do, I believe, in this case, because we're just looking at this one data set. If we were looking at multiple data sets, it might be better to write a function that does this for us. But for this example, I am just going to hard code in the answers. I believe the next most important one would be amount tomatoes, and then after that, it's going to be total customers, and finally, revenue. Now, if we check our answer here, we got it, which is really nice. I'm glad I just did it this way. Save us a little bit of time so we can continue on. The math behind PCA. At this point, we need to address how we can actually take information from multiple features and distill it down into a smaller number of features. Let's dive deeper into each of the steps that lead to PCA. Data matrix. First off, we need to isolate a data matrix. Another name for this is a data set. This data matrix holds all of the features and information that we are interested in, i.e. features and other columns that we want to predict, i.e. labels. Using our previous data set, we have 5 features, right? We have revenue, amount flour, amount tomatoes, amount cheese, and then the total customers one. Covariance matrix. From here, the next step of PCA is to calculate a covariance matrix. Essentially, a covariance matrix is calculating how much a feature changes with changes in every other feature, i.e. we're looking at the relative variance between two features. Mathematically, the formula between two features x and y is covariance of x and y is 1 over n minus 1 sum of x sub I minus its mean times y sub I minus its mean. So we will do this equation for the relationship between each of our features, ultimately resulting in a covariance matrix that shows the relationship for the entire data set. Simplifying our data set, we could think about our pizza data set as having 5 individual features with the name A, B, C, D, E. Our ultimate covariance matrix thus will end up looking like this. Luckily, with the pandas package, we can calculate a covariance matrix with the .cov method. For our pizza data set, result in the following. Seeing a lot of numbers here. One important thing to note is that along the primary diagonal from top left to bottom right, we see the same variance values that we did calculated for each individual column earlier, because obviously we are multiplying the number by itself when we do this. So we'll find that same number when we just calculated it previously, which would be this one, this one, this one, this one, and finally this one. One important point to note is that's exactly what I just said. Nature, factorization, eigenvalues, and eigenvectors. We now have a matrix of variance values for our features. The next step in PCA revolves around matrix factorization. Without going too much detail, our goal is with matrix factorization is to find a pair of smaller matrices whose product would equal our covariance matrix. Another way of thinking about it is we want to find a smaller matrix that captures the majority of our information. An important part of this matrix factorization are eigenvectors. Eigenvectors are vectors, mathematical concepts that have direction and magnitude that do not change when a transformation is applied to them. In the context of our data, these eigenvectors give us a direction to rotate the data set in n-dimensional space so we can look at the entire data set from a simplified perspective. The eigenvalues are related to the relation variation, or relative variation described by each principal component. Okay, for a matrix A, the eigenvectors and eigenvalues are the solutions to the following equation, and we have this. After some linear algebra for our covariance matrix, we are looking for the solution to the following matrix, right? Boom, 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 boom. Principal components. All of the underlying math behind PCA relates results in principal components. But what exactly are they? Principal components are a linear combination of all the output features of the original data set. By using the eigenvectors we calculated earlier, we can rotate our data set features from an n-dimensional space onto... I have no idea why it has now just put a random... Okay, it randomly put a big blue border. I don't know why I did that. Sorry about that. By using these eigenvectors we calculated earlier, we can rotate our dataset features from an n-dimensional space into a two-dimensional space, which is obviously easier for us to understand and analyze. To illustrate this point, let's return to our pizza dataset. We can observe the correlation between revenue and total customers feature by obviously just doing a scatter plot here. End up seeing it looks like as total customers go up, so does total revenue. That tends to make a little bit of sense. We can see the positive correlation between these two features, and that could use that information to guide any analysis we perform. We can also do correlation plots for every combination of features, like so. So this ends up being revenue and revenue, right? We have revenue and total customers, makes sense. Revenue and amount of flour, makes sense. As revenue goes up, product costs are going to go up. The amount of products we need goes up. This makes sense. And of course, along the way here, where it's the same of each, we'll end up spotting that they are very similar. Okay, each individual combination of features will have its own correlation and variance, both of which provide value information about that relationship. When comparing two features at a time, these relationships are more understandable. If we wanted to, however, look at all the feature relationships and information at once, it would be very difficult to decipher as we cannot visualize data in a 5-dimensional space. But by using PCA, we can reduce the dimensionality of our dataset into two-dimensional dataset, allowing for better visualization. Let's see the result. So we, from sklearn.decomposition, import PCA. We create an object PCA, and we set it equal to 2 n components, and then we fit transform our data frame around that. We'll get this array, and then as we can see by running PCA on our original data set, we were able to take our 5 features and reduce them dimensions down to 2 principal components. With 2 dimensions, we can now plot the data on a single scatter plot. So now when we end up plotting this data, we can kind of get an understanding of what this data looks like. While it can be difficult to interpret what this new data matrix is showing us, it does hold valuable information that can be used in a variety of contexts. The axis of this chart are the 2 most impactful principal components as part of our analysis, and they were the 2 that we decided to keep. All right, we got a bit of a fill in the blank here. The below statements outline the overall process of PCA. Fill in the blanks with the correct terms to validate your understanding. Okay, so for a given data set, we start by calculating a blank for all of our features. So I remember the first step ended up being a bit of a covariance matrix. The first thing we did was do the covariance matrix, and then it says we perform blank, which will separate out the data set and give us 2 results. So we wanted to separate out the data. We perform matrix factorization. So principal vectors. Actually, it's not. I believe it's the eigenvectors and eigenvalues. And perfect. Yep, ended up getting that one correct. Pretty happy about that. So for a given, let's read it out. For a given data set, we start by calculating a covariance matrix for all of our features. Afterwards, we perform matrix factorization, which will separate out the data set and give us 2 results. First result is the eigenvector, also known as principal components, which define the direction or rotation of our new data set in our new data space. Eigenvalues determine the magnitude of that new data space. Perfect. So next is the how, where, and why of PCA. PCA serves an important role in many different parts of data science and analytics in general, as this process allows us to maximize the amount of information we can extract from data while reducing computational time down the line. We just saw a common use case of PCA with our pizza data set. We took a higher dimensional data set, 5 dimensions in our case, and reduced it down to 2 dimensions. This 2-dimensional data set can now be used as an input into a variety of machine learning models. For example, we could use this new data set as a part of a forecasting model or perform linear regression. These techniques would have much more difficult prior to performing PCA. PCA is also inherently an unsupervised learning algorithm and can be used to identify clusters in data on its own, very similar to the popular k-means algorithms. Check out last video if you missed it. PCA will look at overall similarities between the different features in a data set. When we set the number of principal components to keep, we are defining the number of similar rotations of our data set, which will act very much like a cluster of their own. Typically, many practitioners will implement PCA as a precursor to other clustering algorithms to augment the accuracy, but it's an interesting application to do clustering with PCA alone. Another very powerful application of PCA is with imaging processing. Images hold a vast amount of information in each file, and analyzing this information can be a very useful application. Image classification, for example, uses algorithms to detect the subject of an image or find a particular object within the image. Overall, it can be very costly to process image data due to the high dimensionality it has. By applying PCA, however, practitioners can often reduce the number of features for the image with minimal information loss and continue their processing. Below are 2 images from a fruit and vegetable image data set. The first image is the original image, and the second image is the reconstructed image using calculated eigenvectors after performing PCA. Note that in this very quick example, there's minimal information loss, meaning that the data could be effectively used for analytics. So obviously a piece of pineapple here, and then they dummied it down here only in black and white, and we can still see it. All right, summary. In this article, you've learned the underlying mathematics behind principal component analysis, PCA, and got a bird's eye view of how, when, where to implement PCA. Principal component analysis is a powerful tool that provides a mechanism to reduce dimensionality and simplify data sets without losing valuable information they inherently contain. The following image summarizes the different applications of PCA, and we are now ready to dive into these in detail. So implementation, I wish this image was a little bit bigger, but it's not, that's okay. So we have a bunch of important information, maybe some redundant information down the line. It's gonna kind of categorize it, right? Implementation, dimensional reduction, so it's gonna remove a lot of the dimensions of it. Information retention, right? All right, we can go next here. Principal components or eigenvectors determine the direction/rotation for data in space. I like that the most, obviously. If you are okay with math, you know that vectors are something that determine magnitude and direction, so knowing that actually helps. When using PCA, you can only produce a resulting data set with 2 dimensions. That's just false, that's not true. It allows for dimension reduction, but 2 dimensions, it's not necessary. It's not strict at that capacity, right? That capability. We do have a data set called data. Would like to perform PCA on it, fill in the code to reduce our data set down to 3 dimensions, and then have PCA model modify the data. Okay, so we'll want to first create a PCA object. We're going to have to specify how many components we want in that object, right? So we'll take 3 dimensions, and to do it, we'll use the dot fit, I believe, it was the dot fit, but maybe now it's the dot modify. It's not the dot modify. I love that it doesn't tell us to. It tricked me there. That was bad wording. Which of the following is not a good use case of PCA? Probably cluster analysis, probably actually this one is not a good use case, yeah. Which of these statistical concepts is the foundation for PCA? Covariance, probably. Covariance is the basics. Which of these following shows the correct format for a covariant matrix with a data set of the 3 features? So we'd want XYZ, and then XXX, XYZ, and then YYY, and then XYZ, ZZZ. Yeah, this one right here. Perfect. What is the main goal of a PCA? To get better features without losing information. Yeah. For a given data set, we can calculate the following coefficients of variation. Determine the most important, least important features for PCA. So most important is definitely going to be this units. I can just see it right off the bat. Least important looks like it's going to be price. Perfect. So we ended up missing one. The actual answer doesn't tell us. Oh, it tells us right. So fit transform. I knew it was a fit. You want to use fit transform. I don't think I could take much more. So now we're going to go into implementing PCA in Python. So introduction to implementing PCA. In this lesson, we'll begin implementing PCA using Python libraries, NumPy and scikit-learn. The motivation of PCA is to find a new set of features that are ordered by the amount of variation and therefore information they contain. We can then select a subset of these features, and this leaves us with lower dimensional data, and that still retains most of the information contained in the larger data set. So, a file named drybean.csv is loaded for you as a pandas data frame called df. Print the head of the data frame. Note that all columns are numerical except for the class column. So we're going to print the data frame head by doing the print statement, df.head, and I'm going to do the first 5 rows. All right. It says, did I print the head? Looks like I did. Maybe it didn't want me to specify 5. Usually I just do 5 because why not? I love that though. I did use head and I got it wrong. Cool. All right, extract the numerical features from df by dropping the class column and save them into a new data frame called data matrix. So we'll do the data matrix is equal to df.drop, and then we'll drop the class. Is that not the correct? Okay, cool. So we've now created a data matrix that has every column except for the class feature. And it looks like when we extract classes here, we're going to want what happens if we print data matrix. I guess I could have just uncommented the line there. Cool. Oh my. Not mean to do that. Make myself radiate here. All right, implementing PCA in NumPy 1. In this exercise, we'll be perform PCA using the NumPy method np.linalg.eig, which performs eigen decomposition and outputs the eigenvalues and eigenvectors. The eigenvalues are, I guess I should maybe check and see if I'm pronouncing this right. I've been kind of confident and thinking that I've been
eigenvalue.
Oh my gosh, I'm just so good. Wow. Yeah, it is eigenvalue. I'm going to assume it's also eigenvectors. It tells how to transform and rotate our data. To implement this in Python, we first create a correlation method on data matrix to get the correlation matrix. So in the data frame you've created, data matrix is loaded. Find the correlation matrix, and we're going to set it equal to the it wants us to find the correlation matrix for data matrix. So we'll do that by doing data matrix.core, and that should end up working for us. Cool. Now, using that correlation matrix, find the eigenvalues and eigenvectors using the NumPy method np.linalg.eig, save them to as eigenvalues and eigenvectors respectively, and then print them out. So we'll do the eigen decomposition. So we'll, I assume, do eigenvalues, eigenvectors is equal to numpy.linalg.eig using the correlation. Oh, come on. Matrix. Perfect. And then we can print these out by just uncommenting these lines here and running it. Oh, wow. Okay. thought it was a little bit less than it was, but perfect. Let's see if the hint did the exact same thing. If I just view solution, I just want to make sure that I'm doing this correct. They ended up uncommenting this, but yeah, everything else was pretty much the same. I should have uncommented this actually. We should see a plot over here. And we do see a heat map here. There are pairs of features with very high correlations, right? So these ones have high correlation. Obviously, along the axis here, we're going to have a very obvious correlation because they are the exact same value. But we also have some cold features, some that are not very correlated, or actually that are very correlated, just on the negative, right? Yeah, nice heat map. All right, implementing PCA in NumPy 2 analysis. After performing PCA, we generally want to know how useful the features are. One way to visualize this is to create a scree plot, which shows the proportion of information described by each principal component. The proportion of information explained is equal to the relative size of each eigenvalue. So if we do info prop is equal to eigenvalue divided by eigenvalues.sum. To see and create a scree plot, we need to plot these relative proportions. So we'll do a plot np.range 1 length of the info prop plus 1 info plot, and then that. End up seeing this. So we see from this plot that the first principal component explains about 50% of the variation in the data, and the second explains about 30%, and so on. Another way to view this is to see how many principal axes it takes to reach around 95% of the total information. Ideally, we like to retain as few features as possible while still reaching that threshold. To do this, we need to calculate the cumulative sum of the info prop vector we created earlier. We could do cum-sum on info prop. We then plot this value using matplotlib and put a horizontal line at 95%. And it looks like at 4 we reach that value of 95%. 4 principal axes account for 95%. All right, the array of eigenvalues is loaded for you. Find the proportion of each eigenvalue compared to the sum of the eigenvalues. Say that result called info prop. So we do the eigenvalues divided by numpy dot sum of the eigenvalues. Did that correct. Now it wants me to uncomment the plotting code below to generate a scree plot. Notice the first axis contained about 50% of the information. So again, we'll do this. And I am just going to run it. It may give me an X here, and that's fine. But here's the scree plot that we got. Next, we're going to do the cumulative sum. So to find that, we do numpy.cum-sum of the variable, what was it up here? Info prop, yeah. Info prop. And then we're going to uncomment this stuff as well. And we end up seeing the cumulative sum happens around 3 axes, so we end up tailing off a little bit more after that. Implementing PCA using scikit-learn. Another way to perform PCA is using the scikit-learn module sklearn.decomposition.pca. The steps to perform PCA using this method are standardize the data matrix. This is done by subtracting the mean and dividing by the standard deviation of each column vector. So we do that by doing mean is equal to data.mean axis equals 0. Standard deviation is equal to data.standard deviation. And then data standardized is equal to the data minus the mean divided by the standard deviation. The standard deviation. Perform eigen decomposition by fitting the standardized data. We can access the eigenvectors using component attribute and the proportional sizes of the eigenvalues using the explained variance ratio attribute. So PCA is equal to the PCA object. Components is equal to PCA fit. So we'll fit the information to the data standardized dot components. And then components is equal to pd.dataframe components.transpose. And then we do some other stuff here and print out the components. We'll end up seeing something a little bit like that. We'll do all this. So the data matrix is loaded for you as data matrix. Standardize all the columns in the data matrix and save the result as data matrix standardize. Then print out the first 5 rows to inspect it. So we want to first standardize the data matrix. So we do this by taking data minus mean divided by stdd, I believe is what we wanted it. Yeah, data minus mean. The thing I believe though, we want to throw this in here, and then it wants me to print out the first 5 rows to inspect it, and that's going to be by uncommenting this line here. I want to say that this might throw an error because there is no just data variable. So I might want to just throw in instead data matrix. So I'll do that, data matrix. Perfect, glad I did that. And now we'll use PCA module from sklearn.decomposition.pca to calculate the principal components eigenvectors. So to do this, we'll save the results as components and then uncomment the code to transpose. So we'll first fit and calculate the comments. Did we create a PCA object? We did. So then we'll do PCA.fit to the data matrix standardized. And the attribute called dot components. Okay. And then uncomment the code to transpose the index. So we'll do that really quick. And see what happens. Cool. So we end up seeing some interesting stuff. You should see 16 eigenvectors. Which obviously we do, 16 rows at 16 columns, right? Perfect. Now using the same PCA object from the previous checkpoint, where you can retrieve the variance information ratios for each principal component using the explained variance ratio property. Save the variance ratios as var ratio and then uncomment the code to resave the data values as a data frame and print them out. Are they consistent with our original finding that the first 4 components account for about 95% of the information in the data? Okay, so to do this, we're going to want to do PCA, just set it equal to this PCA dot explained variance ratio element. And then again, we will transpose it and we can print it out. And we should be able to see that once we get to 4 features, I see, so it's cumulative. So first it goes 55 plus 25. Well, that's about 70%, or sorry, 80%. We add another 8%, we're at 88. By number 3, we're close to 95. I believe it's close. By feature 4, we're definitely there, though. All right, projecting the data onto the principal axis. Once we've performed PCA and obtained the eigenvectors, we can then use them to project the data onto the first few principal axes. We can do this by taking the dot product of the data and eigenvectors, or by using the sklearn.decomposition.pca module as follows. So we can do it if we again specify that we only keep 3 components. We can fit transform it, data frame, column, and then, yeah, okay. Once we have transformed the data, we can look at the scatter plot of the first 2 features. All right, let's Only keep the first 4 principles because they account for 95% of the information in the data. Use the fit transform method to transform the standardized data matrix into the new features and save the result to data.pcomp. So we'll first do PCA, and then I believe it was probably, what is the end features? End features, something like that. End components. Of course, components is equal to, we're going to keep not negative 4 here. And then down here, we're going to do the fit transform method by doing fit underscore transform around the data that is standardized. So data matrix standardized. And after that, it's going to want us to uncomment some of the lines, probably, then uncomment the code to save as a data frame label and print the transform data. So we're going to do that by just doing this, this, and this. And now we should see the table printed out here. We end up seeing all of these elements here, and then uncomment the lines that create a seaborne scatter plot of the first 2 components. So we're just going to uncomment the lines here to see if we can spot some clustering going on. So when we do this, we see a lot of information, but it looks like we do have a little bit of clustering going on, especially in some of these areas here. Very interesting. All right. Let's keep going here. PCA as features. So far we've learned about, we've used PCA to find principal axes and project the data onto them. We can use a subset of the projected data for modeling while retaining most of the information in the original and higher dimensional dataset. For example, recall in the previous exercise that the first 4 principal axes already contain 95% of the total amount of variance or information in the original data. We can use the first 4 components to train a model, just like we would on the original 16 features. Because of the lower dimensionality, we should expect training times to be faster. Furthermore, the principal axes ensure that each new feature has no correlation with any other, which can result in a better model performance. In this checkpoint, we will be using the first 4 principal components as our training data for a support vector classifier SVC. We'll compare this to a model fit with the entire dataset, 16 features, using the average likelihood score. Average likelihood is a model evaluation metric. The higher the average likelihood, the better the fit. So let's read through the code, make sure that you understand what's happening. Here are the steps. So we've imported all our stuff up top. We have standardized our data matrix by just automatically using the standardized CSV. And we're having also a classes. So we have 2 different data frames here. I'm going to use Y as the classes, or classes as Y. Principal components with 4 features, save it as X. We're going to split this data using train test split. 33% testing and the rest training. That's interesting. Let's create a linear support vector classifier and fit it to the model. Generate a score for the testing data. If we just run this code, let's see what happens. Going to take a second because there's a lot of steps here. So looks like when we did the 4 PCA features, our score ended up going above about 4% higher, so obviously better. All right, PCA for images. 1. Another way to show the inner workings of PCA is to use an image dataset. An image can be represented as a row in a data matrix where each feature corresponds to the intensity of a pixel. In this, the following exercise will be using the Olivetti Faces image dataset. If we go here, you can kind of peek at the dataset, and we can get out of there now. Let's start by downloading the Olivetti Faces dataset from scikit-learn. Standardize the image dataset by subtracting the mean and dividing by the standard deviation. So we've done this by uncommenting this line and replacing these question marks with faces mean, and then dividing, of course, by the standard deviation of faces standard deviation. In the second part, it's going to want us to find the side length of the square image. Each row from the faces dataset is a flattened image. Each feature is a pixel in the image. Find the side length of each square image by taking the square root of the number of feature pixels. Uncomment the code to print the number of pixels per image and per side length. So we have this. Boop, boop, boop. Oops. Boop. Okay. So we just have to fix this. We need to do it by finding the square root. So if we just do we have numpy? Yep, we do. So we can do numpy dot square root on the features variable, and then that should work. Perfect. Copy and paste the following plotting code to the bottom of script.py and press run to see the first 15 faces of the data set. So I will do exactly that. We'll paste the plotting code right here. Oh my god, that is absolutely horrifying. But you can actually see it. That is scary as hell. That's fine though. Okay, PCA for images too. Now that we've cleaned up the data, we can perform PCA to retrieve the eigenvalues and eigenvectors. This can be useful in understanding how PCA works. We can visualize the eigenvectors by plotting them. They actually have a name, eigenfaces. The eigenfaces are the building blocks for all the faces in the data set. We can also visualize the dimensionality reduction that occurs when we transform the original data. Oops, sorry about that. The eigenfaces are building blocks. We can also visualize the dimensionality reduction that occurs when we transform the original data using a smaller number of principal components. In the code editor, we have provided the code to plot the eigenfaces, plot the reconstructed faces using a similar transform features. Right. To start, we've used 400 principal components. Press run. First, inspect the eigenfaces and notice how they all depict some of the common distinctive features in the various faces. Now scroll down the plotting output to view the reconstructed faces. These reconstructed only 400 transformed features. So we end up seeing some very interesting stuff over here. I don't even know what to think about all that. Now change the number of components to 40 instead of 400 and press run. So we're going to change this components to just 40 and see how it does. All right. Perfect. Get me out of there. All right. Review. In this lesson, you've seen how PCA can be implemented using NumPy and scikit-learn. In particular, we have seen how implementation, scikit-learn provides a more in-depth set of methods and attributes that extend the number of ways to perform PCA or display the percentage of variance for each principal axis. Dimensionality reduction, we visualize the data projected on the principal axis, known as principal components. Image classification, we performed PCA on images, faces, to visually understand how principal components will still retain nearly all of the information on the original data set. And then improved algorithmic speed / accuracy. There we go. Let's check out what's up next. We do end up having a PCA project, which I'm pretty excited for. So let's get into this. So, so it first says in this project, you will classify particles into gamma, signal, or hadrons background. Given that the features are correlated, you will perform PCA to get a new set of features and select the features that contain the most information. The dataset was generated by a Monte Carlo program. Corsica described in DHEC et al. Corsica, a Monte Carlo code to simulate extensive air showers. I'm not even going to pretend like I can pronounce that. The first part of the project observing the dataset is in script_1.py with its solution in script1solution.py. The second part is in so far. It's highly recommended that you complete the project on your own, blah, 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 blah. So we're going to drop first any NaN values. I'm not going to sit here and pretend like I remember how to do this. It's going to be df.drop something like drop NA maybe? I'm close. I actually very close there. So that's kind of cool. There are so many different like syntax and words for doing stuff. It's like I don't even pretend to try and remember everything. I'll get there maybe one day. Maybe. I don't think so, though. We'll see, though. I'm confident. Let's see. In the second step, it wants us to extract the numerical columns onto a variable named data matrix and classes onto a variable named classes. So, okay. So task 1, drop any NaN values. I guess we can print this out, maybe. It's very nicely formatted. You can see there's some nice lines. Shows exactly. So task 1, we've dropped all NaN values. In step 2, it wants us to extract the classes class. So we can do classes is equal to this, and then data matrix is equal to columns dot, our df.drop columns is equal to class. We can then print this out. So now we see all this. I am going to go up, and as I go, I am going to comment out these tasks as I go so that we're not taking up all this information on this console here. Task 2, we've done. So now in task 3, it's to create a correlation matrix. So we can do this by doing correlation matrix dot matrix dot core, using that, and then it wants us to show it on a heat map. It looks like we should be able to do that just by uncommenting. And it's actually crashing my Google Chrome right now, which is quite interesting. I've actually never had this happen on a Codecademy thing. I've literally never had that happen where it lags like that. So now we can do this. I am going to also just print, or sorry, comment out these print statements. Okay. So here's the heat map. We're now going to find the eigenvectors and eigenvalues. And inside this, we'll throw in the, we want to put in the correlation matrix. So we'll put in correlation matrix, and then uncomment that print line. And I am now going to comment out again this one since we're past it here. So we can just look at this in the console here. Oh, we actually have to, I do not want to comment out correlation matrix dot core. Yeah, that's fine. Cool. Very nice. Step 5, it wants us to find the proportion of each eigenvalue to the total sum of the eigenvalues. So to do that, we're going to order the eigenvalues by ordering the indices using argsort. Okay. Looks like it just wants me to uncomment that to find that. All right, number 5, find the variance information, find the percentages information, dot sum, and then we can do the same thing, percents times 100, I would assume, to make it a percent. Right. And that's fine. Okay, now I'm going to just uncomment this plot so we can take a peek at it. Here we go. And task 6, we're just I'm kind of uncommenting a lot of lines, but following along. We'll throw in the information. And then we could plot it, I suppose. So we got to look at that plot now. So I'll comment that one out. I'm not going to worry about the labels right now, but we will put in the H line and vertical line. It only goes up to task 6, and then it just stops. Oh, it's probably script.2. I'm a little confused by this project. I don't like how it's just me kind of uncommenting and recommenting lines. So I'm going to just skip it for right now. I think we understand the idea of PCA and this PCA project in general. So I'm going to just continue here so I'm not sitting here wasting your guys' time. And we are going to be done with that video then today. So again, we finished the machine learning fundamentals section. I'm really happy about that. We're making really good progress on it. And we'll be able to continue on with some interesting stuff in software engineering for machine learning / AI engineers next. So if you did enjoy today's video, please be sure to give it a like, subscribe, and I will see you in the next one. Peace out.